Okay, so our next presenter is Leonidas Kosmidis, presenting the RISC-V METASAT Multicore and GPU space platform and its software stack. Go ahead.
Hi, everyone. Can you hear me? Perfect. So I'm Leonidas Kosmidis. I'm a senior researcher at the Barcelona Supercomputing Center, and I'm also teaching at the Politècnica University of Catalonia. And in this presentation, I'm going to talk about a project which I'm coordinating. It's called METASAT, and we will talk about the hardware and the software platform that we are building. METASAT is a 2-year horizon project funded by the European Commission. It's about to end at the end of this year, and we are focusing on low TRL technology. In total, we are 5 partners. We at BSc, we are the coordinators. We are building the hardware and the software infrastructure, but we are also contributing in the model-based design tools and in some use cases. We have also Fentis, a small company from Valencia, which provides the Extratum hypervisor that we are using in the project. We have Collins Aerospace, which provides the co-simulation infrastructure and contributes to the model-based engineering workflow. We have Ikerlan, who provide support for model-based design tools, and OHB, which provide the space use cases that we are using. Some motivation about our work. Modern and upcoming space systems require more and more performance, which cannot be delivered by existing space processors. So we need more high-performance hardware in space. The reason is that we have heard all these days about more autonomy. We want to run artificial intelligence on board. We have high-resolution instruments. We want to process data faster and so on. So in order to implement all these complex functionalities, we require more complex hardware and more complex software than what we are currently using in space. In particular, in hardware, we need high-performance hardware technologies like advanced multicores, graphics processing units, and AI accelerators. And in order to take advantage of this complex hardware, we need also complex software like parallel and GPU programming. We cannot afford using those multicores with sequential processing anymore. For this type of complex applications, single-thread performance is not enough. A way to manage the complexity of the systems is by using model-based design, which can reduce the development and verification time. In this case, we start with high-level models, and then we can automatically generate code which will be correct by construction. We can verify them in multiple different levels. We can start with model in the loop, software in the loop, and processor in the loop. And we can take advantage also from virtual platforms and virtual twins, so that we can start the software development before the hardware is ready, and we can break this weight dependency between hardware and software. We have seen a couple of talks on this already. The problem was that in order to showcase this methodology for this complex hardware, there was no space hardware with such architectural complexity that we could use. One possibility could be to use COTS-embedded multicore and GPUs, like the ones provided by NVIDIA in the Jetson family. However, the problem with these devices is that they depend on non-qualifiable software stacks. If we want to use the GPU, we need a GPU driver, and GPU drivers are only available from these companies for Linux. So this is a blocking issue if we want to adopt this type of devices for institutional missions. So the only solution was for us to implement our prototype in a hardware platform, leveraging the RISC-V ISA. Here on the bottom, you can see an overview of the architecture that we are designing. We have a multicore integrating a small vector unit and connected with a GPU. One of the concepts that we leverage in METASAT is virtualization, in particular time and space partitioning, again mentioned many times during this workshop. The benefits are obvious: faster and easier integration. We can develop and test different components in isolation, and also we can implement fault detection, isolation, and recovery easier. In the project, we are using the Xtratum next generation hypervisor by Fentis. This is already qualified for category B according to ECSS, and it's flying in several CNES and ESA missions. Also in METASAT, we use open source and standardized technologies because we want to maximize interoperability and avoid vendor lock-in. We want also to facilitate the development of a space ecosystem. On the model design side, we are using ESA-based open source model-based design framework, which we modify in order to add support for code generation for high-performance platforms like multicores and GPUs. And on the hardware side, we are also leveraging the open source processor technologies, in particular from Geissler, the Noel5 RISC-V processor, which we have enhanced with AI processing acceleration capabilities. Our platform is designed for mixed criticality, and it's prototyped on a Xilinx VCU118. On the CPU side, we have a multicore based on Noel5, and we have integrated our own short vector accelerator, which is called SwRI. With this part of the architecture, we want to have high criticality software, fully qualifiable, with a fully qualifiable software stack that has moderate AI acceleration needs. Some words about our SwRI accelerator. It's a short vector unit co-designed for the acceleration of AI workloads. It can provide high performance, and at the same time, it has very low hardware utilization. It's at least 30% smaller than conventional vector processors that provide similar performance. And one of the main benefits is that in order to integrate it with any core, it requires minimal modifications. So this is very helpful in our industry because it can provide incremental qualification. Some of the key features that we support is the reuse of the integer register file of the processor, which contributes to its low cost. It supports 8-bit short vector operations, swizzling, and reductions. And we have a programming model very similar to intrinsics like ARM's Neon in order to program this. Currently, we are in talks with Geissler in order to adopt SwRI as part of the next space processors. Now, let's see a bit on the GPU side. There, we are also using a RISC-V open source GPU. We are using Vortex. It's an open source project from Georgia Tech, which we enhance with real-time execution support for worst-case execution time and for reliability. We target to have a fully qualifiable software stack, now for tasks that require higher performance than the ones that can be run on the CPU, and to enable the use of GPU from bare metal or from a real-time operating system, and allow the different partitions in the system to share the GPU. At the end of the project, all our hardware and software developments are going to be open source, with the only exception of the hypervisor, which is proprietary. Now let's talk a bit about the current status of the project. First, I will talk about the FPGA resource utilization. Here, I would like to emphasize that at this stage of the project, we don't really care about performance. We want to have a functional platform in which we can demonstrate all the software running and all our model-based workflow. Although, as we are going to see, we already have, with this design, a quite high performance. So in the configuration we are using currently, we have a 4-core multicore based on Noel5. We are using the high-performance configuration, which includes dual issue, floating point, the FP Lite low cost and low performance GPL version of the floating point unit from Geissler. We have full support for a hypervisor, and we integrate in each core 2 Sparrow accelerators, one for each of the dual pipelines. We also use the L2CAS Lite, again, is part of the GPL version of NoL5. And again, it has a lower performance than the commercial one that Geissler uses in their commercial products. We have our GPU, it's 64-bit RISC-V processors with vector extensions. Currently, we have a configuration with 2 compute units and 4 threads, but all the things that I have shown here are configurable. So in the end, we are able to configure the number of cores, the sizes of the cache, how many levels of cache we want, the number of compute units or threads supported. It's just we needed some small design that we can synthesize. I can tell you that this design takes more than 6 hours to be synthesized. And also, if you want to simulate, to debug, it's better to be small. In addition, on peripherals, we are using the GR Ethernet IP, again from the GR-Lib from Geissler and UARTS. And later in the project, we are going to do a space exploration in order to find what are the best parameters for our use cases. Here you can see the floor plan of our FPGA. Almost half of the design is occupied by our multi-core CPU. You can see here on the left the memory controller for the CPU and the 4 cores, and a small L2 cache. And here you can see the Sparrow units. You can see that they are quite small compared to the size of the cores. The other half of our design is occupied by the GPU. We have the memory controller for the GPU here, 2 compute units and instruction and data caches, and the Axilite controller that interfaces the CPU and the GPU. Now let's talk a bit about the status of the software. As I said, we want to have parallel programs running, and for this we take advantage of OpenMP, which is supported in RTEMS. Now we are able to run OpenMP workloads on both the FPGA and the virtual platform that I will mention later, under RTEMS with and without Extratum. And we have also published some performance results. We have compared the multi-core capabilities of promising candidates for next generation flight computers. You can see the link of our publication on the bottom. And we compared also against an existing processor, space processor, the GR740. And we got really promising results, considering that we have a design running on an FPGA. We have 100 megahertz clock, and we were comparing with ASICs. And in fact, in 8-bit processing, which is required for AI, we exceed the performance of the GR740. We have full support for Sparrow, both in RTEMS and in the hypervisor. We modified the RTEMS compiler and also the context switch routines in order to have support for the control register. And currently we are working on TensorFlow Lite and TensorFlow Micro support so that we can have accelerated layers using Sparrow. Now I would like to show you some performance results. Here we use matrix multiplication on RTEMS. Matrix multiplication is an essential building blocks for all AI operations because it's used for modeling dense layers and also in convolutions. And here we can see for 2 different sizes the results. Here we have a single core, and here we can see the performance we get only using 4 cores, using OpenMP, almost linear scaling. This is something very important that we have noticed. We compared performance with OpenMP on Linux and on RTEMS, and almost for all our workloads on RTEMS, we get linear scaling with a number of cores, which is not the case in Linux. And here you can see also the comparison of a single core execution only using Sparrow. And here we can get 6 times speed up compared to the single threaded execution. And if we combine both, we can get more than 20 times faster execution compared to single threaded performance. So something really interesting is that, as I showed you in the previous slide, Sparrow is very small, but can provide higher performance than 4 cores. And also that we can combine both a multicore and vector to get more than 20 times speed up. Now let's talk a bit about the GPU status. It's fully integrated with the multicore. We needed to add an AXI interface for that. And at this stage, we're able to offload computations from the CPU to the GPU, and we can do that in bare metal, in RTEMS, and also under the hypervisor. We have defined a programming methodology to do so. We precompile the GPU kernel, and this is a common practice in all safety-critical systems APIs, like the Kronos, OpenGL safety-critical, and in Vulkan safety-critical. And we embed the GPU binary in the program executable. We needed to do that because when we run in bare metal, we don't have any file system to load from. And we achieved that with linker script modifications. Currently, we support the Vortex GPU API, which is a low-level programming model. And we are also working on higher performance, higher abstraction programming models like Brook Auto, which is a qualifiable GPU programming toolchain we have developed at BSc, as well as OpenCL and OpenGL safety-critical too. Also, we are able to leverage code generation from MATLAB Simulink. With GPU Coder, we can generate CUDA code, and we have built a translator from the CUDA-generated code to Brook Auto. Here you can see a small video of pre-recorded video of a demo. We have matrix multiplication running on the left on the multicore and on Sparrow with increasing sizes. And on the right, you can have the same, but running in the GPU, and it's much faster, as you can tell. Apart from our FPGA design, we also have a digital twin. So we have a virtual platform. The multicore is modeled in QEMU, and currently we are working to have full support for Sparrow. And for the GPU side, we are using Verilator, which is a very fast cycle-accurate simulator that converts System Verilog to C++ and System C. When we started with this work, as an exercise to get familiar with QEMU, we started modeling the GR740 and the GR712, so they are nice byproducts of this work. We have a model in which we model quite accurately the peculiar GR740 GRFPU, and we are able to run unmodified Linux and RTEMS binaries that we can download from Geisler's website. We continued this work with modeling Noel 5 and also our METASAT platform. Again, we are able to boot unmodified binaries. And we have also now support for Sparrow and for the L2CAS Lite controller. Here in this link, you can download a tutorial. We have packaged everything in a nice Docker container, and you can play with the platform and with Sparrow. And if you would like any assistance, just drop me an email. We also added support for RISC-V in taste. So we are able to generate code, skeletons of applications in RTEMS, compile them with a RISC-V compiler, and also run them on our own QEMU simulator. And before closing, I would like also to mention the use cases that we are going to have in the project. We are going to have 3 different use cases. The first one is provided by OHB and DLR. So currently they are porting their flight software to our platform. And in addition to this, we have some functionality that currently are implemented in hardware, but now we saw how with model-based design, we can move this to software and we can reduce the cost. And also we are implementing AI-based FDIR, which is going to be accelerated on the CPU side on the Sparrow AI accelerator. And for that, we are using real housekeeping data from the NMAP mission of OHB and DLR. Also, we wanted to use cases that make use of the GPU, and no flight software so far use that. So for this, we provide two use cases from BSc based on the OBP Mark open source benchmarking suite that we have developed for ESA. The first application implements cloud segmentation, identifying clouds in satellite images and removing them, and ship detection from satellite images. Yesterday, Pablo from Clepsydra have already shown you some demos that we have done in collaboration. And also feel free to check our flight software workshop pre-recorded video about this cloud screening application ported to ESA's OPSAT. To conclude, in METASAT, we achieve a major milestone towards the use of GPUs and high-performance platforms in space. We provide an open-source reference hardware platform, both in an FPGA prototype and in digital twin, and that could be a possible starting point for a future tape-out on a radiation-tolerant or radiation-hardened process. We solve key limitations preventing currently GPUs to be adopted in institutional missions. We are having a fully qualifiable software stack. We have promising early results, and soon we will evaluate our platform with relevant space use cases. And with that, thank you very much for your attention, and I will be happy to take any questions.
One second. Is that me? Okay. You do hear me. Okay. So could you say more on why the NVIDIA Linux 4 Tegra software stack is not qualifiable?
It's just because of Linux. I mean, agencies, I know that Linux is more embraced by industry, especially in new space. This is not a problem. But when we talk with space agencies, they are very reluctant in high criticality missions to adopt Linux. For example, I can talk about ESA that I'm more familiar. Until recently, there were just 3 classes of missions. In none of them, Linux could be used. Recently, they revised that, and they added 2 more classes, class 4 and class 5. Class 5 is new space. We can use anything. Now there is some discussion that maybe it could be acceptable to use Linux in class 4, provided that some additional provisions are taken. So yeah, we want to play safe. We want to enable the use of GPUs in any mission, and that's how we try to do it.
How is Sparrow programmed? Directly in assembly, or is there some level of support by a compiler?
Good question. So currently we have 2 ways to program it. So one is directly in assembly, which is quite low level. We recently added a library which provides an intrinsic-like interface, the same way that you program Neon or SSC in x86. And yeah, in the future maybe we will add more support for compilers.
What are the data types supported by Sparrow and the GPU? Which one was used for the matrix multiplication benchmarks?
So for the ones that I showed you, I mean, in Sparrow we are limited to 8-bit because it's co-designed specifically for AI inference. And almost everywhere in AI acceleration for the edge, they use 8 bits or less. So that was the data type that we have used. But for the GPU, we don't have this restriction. We can use even floating point and yeah, any data type that it's available in C.
Okay. Could you share how the naming process went for your GPU toolchain? The Brazil?
Yeah.
They like the name, so I suppose it's coming
Cool.
from over there.
Thank you. So yeah, let me find which one was the slide. No. Yeah, this one. So yeah, there is this language which is called Brook. Brook was a project started in Stanford back in 2004 when people realized that GPUs were powerful enough. But at that moment, people were just trying to map general purpose algorithms to graphics, and that's onerous. So there was this project, open source project called Brook, that translated from CUDA-like language to OpenGL. Later, the leader of this project moved to NVIDIA, and now he's leading the CUDA development. That's why the two languages are quite similar. We adopted this open source project, and we added support for OpenGL ES and OpenGL Safety Critical. And then later we did this study about how to qualify this tool according to ISO 26262 functional safety standard for automotive. And in automotive, there is a concept of ASIL, which provides the criticality of software. So Brook and ASIL, it's Brazil.
Thank you. So I've got one last question. Sorry, I lost it. One last question. Are there any blocks in the GPU, for example, used for rendering, which could be removed to save space in the FPGA if all you want to do is run OpenGL CL kernels?
Very good question. So actually, there are two versions of Vortex. Vortex, it's purely GPU design, so it doesn't have any graphics stuff that we don't need. But there is also another variant of Vortex, which is called Skybox. And on the other hand, it's just developed for graphics, so we can leverage both. In what I have shown, we are using pure Vortex, which is pure GPU.
Awesome. So there's at least one other question on the thread. Please follow up. Thank you very much.
Thank you.